Hey, welcome back to more calculus, and today is our second day looking into optimization problems, and let's just hit the ground running. Let's get going over to the zombies. So, inspired by many cartoons, you have decided to create a giant zombie box trap in order to capture, of course, the zombies. You're going to make a box that's basically an open top box like this. You're going to invert that box and hopefully catch us some zombies. You're going to make that out of a 7 by 10 meter piece of scrap metal. That's admittedly a really big piece of metal. And you're going to fold up the sides. Cut out the corners and fold up the sides. And if you want to maximize the volume of the box, how big of a square should you cut out of each corner? So that's a really interesting question. Here's our strategies for optimization here. And let's draw ourselves a 7 by 10 piece of metal just so we can kind of understand this. So here's a piece of sheet metal. It's 7 by 10, as you can see. We're going to cut out squares in the corners of this box. So cut those out, and the dimensions of those squares, well, those are all going to be x by x. So that's going to kind of help us think about this with our domain of x. And let's do the 10 side first here. So how big could I cut out a square here? Well, I probably can't go more than 5 meters, because if I make more than 5 meters, let's say I cut at 6 meters here, that means that I'm going to cut 6 meters by 6 meters here like that. And I'm also going to cut 6 meters by 6 meters here like that. And there's just not that material there. You're cutting out the same piece of scrap metal a couple of different times. So that's not going to work. And let's say, okay, well, that works. Well, that doesn't work. So why don't we try cutting out a 5 meter by 5 meter square? Because 5 is half of 10. Okay, now that's kind of more sensible. We'll cut 5 meters out of this corner. That's cool. 5 meters off of this corner. And then we'll also cut 5 meters off of this corner. And I think you see the problem. We're cutting out this piece right here a couple of different times. So 5 meters doesn't work either. Okay, so clearly we're playing with the wrong side here. What if we cut out half of 7? Okay, half of 7 is 3.5 feet. So 3.5 feet would be something like that. Cut out this corner, cut out this corner, and cut out this corner. Okay, well, that's not going to make a box, but it doesn't need to. That's theoretically the biggest cut we can make is 3.5 feet. So we've found out that x has to be between 0 and 3.5 feet. You're always constrained by your smallest dimension. That's a good thing for us to remember. Look at your smallest dimension if you want to constrain yourself, if you want to figure out the biggest thing you can do. So let's move on from there. Here is our box again. And let's figure out our second equation. Now, the secondary equation for length. How long? Well, that's the entire length. That's our 10 meters. The length that we need is this right here. How long is that? And if this is x here, and this is x here, then the yellow thing, blue plus yellow plus blue, that all has to add up to 10 meters. So then the yellow is 2 as x. Sorry, the yellow piece is going to be 10 minus the 2 x's. Similarly, on the other side of things, if this is going to be this side of the box, then we've got this is an x here, and this is an x here. Since all three of those segments have to add up to 7, the yellow piece is going to be 7 minus x, or 7 minus 2x. And lastly, what about the depth of this box? Well, remember, we're gonna fold up over here, and then this side over here that I'm marking in green, that's going to be this part right here. Okay, this front part, I'm going to do this in blue. I hope that that's not going to be too distracting. This front part is going to fold up along the line, and that's going to be this piece right here. You probably can't see me making that blue, but this piece right here. And then the back is, let's do that in yellow. The back piece is going to be this one right here in the back, tucked out back there. And then finally, let's get a different color highlighter. Let's do purple. This piece right here on the side, that's going to be this wall right over here. That's barely visible. And then, of course, the bottom of the box is going to be this center portion right here. So that's how that's going to work. It's going to fold up. So the depth, how deep is this going to be? Well, this dimension right here, that's going to be x, because that corresponds, let's see, that corresponds with this piece right here. So that's x tall. Now, all three of those equations, or I should say none of those three equations, are actually going to give me the thing that I'm trying to figure out, which is the volume of the box. So you probably notice down over here, we have a primary equation, which is the volume of the box, which is length times width times depth. That's the volume of any, this is a rectangular prism, so any rectangular prism. So we'll relabel that as f of x, like always. And we'll substitute into that our three secondary equations, is what we usually call them. You don't have to worry too much about that bit of vocabulary, but you might hear me in class talk about secondary equations. When you make all those substitutions, you get x times the quantity of 10 minus x multiplied by the quantity of 7 minus 2x. And when you expand, you'll get 4x cubed minus 34x plus 70x. So once again, 4x cubed minus 34x squared plus 70x. So this is our volume function. This is the thing that we're trying to optimize. And in this case, optimize means maximize. So next, we're going to mark, label, and estimate. Where is 0, f of 0? That's right over here. Notice our volume there is 0. So that's the smallest possible height of the box. So remember, our box, the height of the box, the depth of the box is that x coordinate. So when x is 0, the volume will also be 0, and that should make sense based on all of the things that we did. What about 3.5, f of 3.5? We talked about f of 3.5 earlier, or we talked about 3.5 meters anyways. That was special because that was the biggest cut that we can make into that sheet metal. So that is, quote, the largest possible height of the box. And notice that we're not quite sure what that volume is going to be, but based on what I'm seeing on the graph, the volume here is going to be 0. And then finally, what about the maximum value of f of x? If this graph is the graph of f of x right here, then the biggest possible volume of f of x is about 42.37 when the cut on the box is 1.352. Again, that is a graphical solution. That is not the calculus solution. We're here to figure out the calculus solution of solving this, because you're not always going to be able to graph your function, let me tell you. So let's scroll and see what we got here. The minimum value of x, we talked about that. That's 0. The maximum value of x, we talked about that. That's 3.5. And then the domain for x, we haven't talked about that explicitly, but we should know, if we know the minimum and maximum value of x, we should also know that x must be between the minimum and maximum. So x should be between 0 and 3.5. We talked about what f of x was. It was 4x cubed minus 34x squared plus 70x. We get that from expanding our polynomial. Now that we have this as a polynomial, the derivative is pretty darn easy. It's just 12x squared minus 68x plus 70. Now that is a second degree polynomial. So if I set that equal to 0, like we do in part C, equals 0, we need to do some quadratic formula. So we got 2x squared minus 34x plus 35. And we do some quadratic formula. And we get 2 roots. The 2 roots are 1.35196 and 4.31. So let's go ahead and put these into our calculator and see how could we get that without using a quadratic formula. How can we solve that equation with the calculator? Last time we talked about solving this graphically, and I'll just briefly do that. Here's our equation in y1. Our window, let's remember that x must be between 0 and 3.5. And last time I kind of made a big deal about the derivative and what the y min and y max is. And really, it doesn't matter what you put because you're looking for where the graph of the derivative crosses the x-axis. So you have to have some positive and some negative. If the graph goes off of the window, that's not really a big deal because you're only concerned about when the derivative is equal to 0. Remember, that, I'm saying this because we're graphing the derivative. So let's graph the derivative, and it should hit 0 right about here. I don't care what happens anywhere else. I can see the derivative is changing from positive to negative. So that means that I have a relative maximum. Let's copy and paste this into my work. And we're going to see that here, the graph of f is positive. Here, the graph of f is negative. It doesn't matter. I'm going to do that all over again. Up over here, the graph of f prime is positive. Down over here, the graph of f prime is negative. Since the derivative changes from positive to negative, this is indicative of a relative maximum. Now that we know that that's a relative maximum, that kind of takes away a little bit of our mental stress, I guess. Let's go back to the calculator and let's figure out the coordinate there. We can go calculate the 0. Let's see, that's between 1 and 2. So the left bound, I'll make that a 1. Right bound, I'll make that 2. Make my guess at 1.5. And that gives me 1.35196. Okay, so that's going to be my critical point. How else can I solve for that 1.35? First of all, before I do that using the solver, let me just say that this method right here graphically is really good because it not only tells you the critical value, it gives you an idea about whether or not the derivative is positive or negative. You don't have to do any test points or anything. You already know. But if you insist on learning how to use a solver, and why wouldn't you? On this calculator, you have two things. You have you have E1 and E2. In E1, you're going to put the left side of the equation. Like if you're writing out the equation, the left side of the equation. So what I want on the left side of the equation is I want y1. Y1, if you remember, was this equation, the derivative. In E2, we want to set the derivative y1 equal to 0. So basically, these two boxes say y1 equals 0. Then I'm going to OK, or just use the down arrow. And here, I know that the answer is actually 1.35, but what you need to do to solve is just put any number here that is close to the actual point. So I'm going to say 1.5 is my guess, just like I did before with the graphical method. Take a guess of 1.5, and then to make it solve, you need to push alpha and then enter. And that's going to go ahead and give me the correct root when y1 is equal to 0. Up over here in the window, it tells you what you're solving. You're solving y1 equals 0. Now, this has a couple of fatal flaws. Number one among those fatal flaws is if there are more than one solution, then you're going to only get the solution that's closest to your guess. So what I tend to do is I try a bunch of different places along the domain. Let's try it 2, and let's alpha solve that. And that's going to give me the same solution. Let's try 2.5. Try that again. And if after you've tried at multiple places in your interval that you still come up with the same solution, then that's going to be the only solution. Oh, we didn't try 0.5. Maybe there's something close to 0.5. So I think you can see that sometimes the graphical method is, well, a lot of times the graphical method really is superior to using the solver, although the solver is nice because it is a quick thing to do. So let's take a screenshot of this and move on. Okay, that looks good. And let's go ahead with our analysis here. F prime and F. And I'm going to go ahead and complete this chart. Those are the other two numbers that we want to use to figure out our candidate test. Let's go ahead and get back to the calculator. So I'm going to go ahead and put the function for volume in Y2. Do my table set, make sure that I'm still on independent ask. That is good. Let's go to our table and let's substitute and make our table our candidate test table. 0, we had 3.5, and then we also had 1.35196, and that gives me so y1 is the derivative, y2 is the function, so the function I get 42.377. Now that's probably not enough accuracy, so if you cursor over to that, that'll give you more digits for your table. So let's go ahead and copy that information on our table. And let's make an analysis. 0 and 0. The volume is 0 when the cut is 0. The volume is also 0 when the cut is 3.5. So analysis on that. Those are both minima. And finally, when the cut is 1.35196, the volume is 42.37656, which is my maximum volume. So that is really all of the analysis that we're going to need here. Let's interpret our solution. When x is 1.351, f of x is 42. So the zombie box trap has a maximum volume of 42 and change when the side of the square cut from the scrap metal is 1.35196 meters. So look, we did a lot of calculator work today. Hopefully using the calculator in this way is going to be very beneficial to you. So make sure you're learning all of these techniques. Which brings us to our important ideas. Secondary equations tend to only have one variable, while primary equations will have both independent and dependent variables. Independent variables and the dependent variable. You're going to use your secondary equation to reduce your primary equation to an equation of only one variable through substitution. For problems involving physical objects, you're going to choose the domain for x so that all dimensions are positive. To achieve this, focus on the smallest dimension of the object. Okay, so that is key. We talked about that earlier. And so you only need to test the critical values that are in the domain. Let's take a look at, or I'll pause here for 1 second. You want to screenshot that, or if you want to write that down. And let's get to checking our understanding. So the height of a projectile, perhaps aimed at a zombie, is given by s of t equals negative 16t squared plus 96t plus 112. Find the time when this projectile hits the ground, that's s equals 0, and find the maximum height of this projectile. So this projectile is some kind of a mortar shell or something like that. Surface to surface artillery. Okay, I'm just thinking out loud. Let's develop the mathematical model of this problem, and really there's not a whole lot to do here. The mathematical problem in this case is already given to you. It's s of t equals negative 16t squared plus 96t plus 112, where s is the height of the projectile. Okay. Graph the function. We've kind of graphed that function, and we can see that the height of the projectile is 0 at 7 seconds. That's right down over here. 7 seconds, our height is 0. And of course, the lowest value of t is going to also be 0 because, negative time doesn't really mean anything to us here. Let's identify our critical points and our endpoints. If s is our function that we're going to maximize, then we're going to need to do a derivative analysis. So s prime is going to be equal to negative 32t plus 96. Set that equal to 0, and we get t equals 3. So t equals 3 is our critical value. Our endpoints are 0 and 7. Let's do a candidate test, and I think it might be fun to do this with a calculator. So let's grab our calculator. Okay, we haven't done anything to it, so we'll go to y1 and, the y equals menu. And here, let's clear everything. y1, we're going to put in our we're going to put in our height equation. We don't need the derivative because we've already done our derivative analysis. We already know our critical values. So let's go to our table and let's substitute things in. Our domain is 0 to 7. That gives me an initial height of 112, and at t equals 7, the height of the projectile is 0. And we'll put in our critical value, which is 3. That gives me 256. So it looks like the highest height of this projectile would be 256. Now I think this is the first time we've seen it where the left endpoint is not 0. So the left endpoint here, when t was equal to 0, we very easily could have had that as either the minimum or the maximum. In this case, probably the maximum, but it didn't turn out that way. We'll just put our calculator work on the side over here. And here's our analysis, t equals 0. Well, this is the exact same thing. Our analysis is we have a maximum height at s equals 3. The maximum height is 256. We have a minimum height at t equals 7. The minimum height of the projectile is 0. Now let's interpret this. Part A, the projectile is going to hit the ground at t equals 7 seconds. And part B, the projectile is going to reach a maximum height of 256 feet when t is equal to 3. So that does it for us here. Hopefully, if you learn anything here, I think the calculator functions are a really good thing for you to go on. They really help you, especially, for these more intense functions. And we'll see you next time here with more calculus lessons. Have a good day.